All right, how's it going, everybody? I am making this video here on Saturday, May 1st, and today we're going to talk about section 6.1, Laplace transforms. This is going to be our final chapter that we're covering this semester here. We're going to look at 6.1 and 6.3 as our two sections exploring Laplace transforms a little bit. And what you're going to see is that the stuff that we're going to cover this week completely different than everything that we've looked at otherwise this semester. It at least still follows the same vein that our goal is to solve differential equations, and it's using the recognition that differential equations are difficult to solve because of lots of issues associated with integration. So our goal with these Laplace transforms is to build a tool that's going to help us solve first and second order differential equations, and it's going to avoid lots of the issues that we generally have with a general version of these things, such as our inability to perform required integration, our inability to fit the differential equation into some known format. I mean, what did we do? Spent 5 weeks looking at like linear systems of differential equations. That was a really specific format. As soon as we got out of that format, all of a sudden we couldn't directly use the math that we had learned in those cases anymore, right? So it's this often desirable thing to say, well, if I can get my differential equation to look like this structure, then I know all these different things about it. Well, if you have a differential equation that you can't fit to some known structure, then you're usually kind of high and dry on that one. You usually, you've got to kind of invent your own route to solving that thing, and that's going to be challenging. The other issues that come up is when we discuss functions that have discontinuities in them. We're not going to discuss that too much here, but it is one of the issues that does crop up with these things. And in that case, I think that you should think about like our forcing functions and even just pushing the child on a swing. What you know in those contexts is that we give a push and we go from applying a force to as soon as the child leaves our hands, all of a sudden we're applying no force right there. That's not just some like smooth sinusoidal force we're applying right there. It's really like we're applying a force that sort of like drops off to zero for a short period of time and then picks right back up to there being a force again when we start doing the push again. So really we should be thinking about that being like a discontinuous forcing function right there. Turns out Laplace transforms handle that stuff very conveniently, whereas traditional calculus techniques do not. So, what our goal is going to be in these sections here in chapter 6 is that we want to say, listen, calculus brings us a whole host of issues with attempting to solve these differential equations. So, what we want to do is we want to avoid doing the calculus. We're going to put the calculus in a different component of the solving structure in a place where we can manage it a bit more directly. So the goal is going to be to convert our calculus operations that we would have to do with our differential equations into just algebra operations so that we can do them very, very simply. Then we'll undo the transition into a new setting that we've done to arrive back in our original format for an answer. To do all this, what we're going to do is we're going to come up with a function or an operation that is going to measure how much one function is like another function. And so what we want to do is we want to kind of explore this a little bit on our own first, and ask ourselves, because I think it's slightly natural to come up with this idea. This is a weird idea, but I don't think it's so weird that we couldn't at least think about kind of some of the ideas associated with it. So let's kind of ask ourselves two kind of basic questions about functions being the same. And so we're going to look at a graphical example and an algebraic example. And the thing that we want to ask is, how would you measure the similarity between two functions? I want to get a numerical measure of how similar two functions are. So in this, we see two sets of graphs. In both of these graphs, the orange curve is the function sine of t, and the blue curve is some other function that we're comparing to sine of t. And I want to say to you, how similar are the blue and the orange curves? Hopefully it's very obvious that you should be saying that in the first graph right here, the blue and the orange curve are very similar to one another. They're highly similar. They almost fully agree. And clearly in the second graph, they fully disagree. They're doing literally opposite behavior as one another. So here we almost fully agree with one another. And here they fully disagree with one another. So my question to you, and you should stop and you should really think about this for your own a little bit right here, is saying, how would we do a math operation, a calculation, to compute a number that helps us judge how similar these two functions are? A lot of students' first instinct in this setting is to suggest that we should perhaps perform some subtraction, because that would be measuring how much of a difference there is between two functions. Unfortunately, we're not trying to measure how different our two functions. We're trying to measure how similar our two functions. You should notice that if we perform subtraction between the orange and the blue function, for example, in our first graph right here, then we'd be getting a whole lot of numbers that are zero, really, right? That would be indicating a very small number. And that's sort of the opposite of what I'm interested in. I'm sort of thinking to myself, I should be coming up with large numbers when we're very similar, and I should be coming up with small numbers when we're very dissimilar. You should also notice that if we performed subtraction between the two functions over here, it's essentially like doubling the function. If I took the orange function and subtracted off the negatives associated with the blue function, I'm actually going to be getting values that are twice as large as they were before. And I don't want large values when we're similar or when we are dissimilar. I want small values when we're dissimilar. Another idea that you might have then is to notice that perhaps doing some multiplication between these two functions is perhaps a slightly better way to go ahead and measure that similarity. You should notice here that these two functions, for example, at pi halves, both of these functions are almost 1. So in this setting right here, in this lobe of these two functions, they're both positive, and when we multiply positives times positive, we get more positive numbers, and we're going to get large positive numbers when they're both large at the same time. You should also notice that when we're looking at, for example, this lobe down here, both of the values of both of the functions are experiencing negative values. And so when we take their product, we're actually going to get more positive numbers right there, right? So that's contributing to this idea that's saying we will get large numbers out when we do the product of both of these two functions right here. Looking at the second graph, the second pair of functions over here, you should now notice that in all of the multiplications that we do between the orange and the blue curve, in this case, it is always the case that one of the functions is positive and one of the functions is negative for any given x value, with the exception of the locations where both functions are zero. And consequently, we're always going to get negative numbers out from the product of the orange and the blue curves right here, always. And that negative value is indicating to us a dissimilarity, which is exactly what we're seeing right here. Now, when I say the product of two functions, sort of what I'm suggesting is we want to accumulate all of the products of these two functions right here, saying I might want to look at this x value and say, look at the product of these two functions at this given x value. Add it to the product of these two functions at this given x value. Add it to the product of these two functions at this given x value here. Well, what that's saying to me is I want to sum up all of the products of these two functions over all of the x values of interest. It sounds to me like I'm actually just describing an integral right there. I want to say here differences do the opposite of what we want. Instead, if we sum the products of the two functions, we'll get positives when the functions are similar, and small or negative numbers when dissimilar. And so it seems to me like a sum of the products is a good way to go of looking at these guys here. And that really means to me something like the integral of, and notice again here we had the orange function was sine of t, and the blue function was some unknown function right here. So here I might write this as the integral of y of t, the unknown function, times sine of t dt. Because the orange function was the sine of t, and maybe I can kind of colorize this a little bit here for us. Right, there's our two functions that we were interested in, the unknown y of t and the blue function sine of t right there. And again, this is just an idea. We're talking about something kind of weird right now. And so I'm just kind of saying, like, I don't know what seems good. I at least kind of talked myself out of doing subtraction between the two functions. And it does seem to me like, especially when these functions are centered around the x-axis, that multiplication seems to be a decent representation. And we would want to know across all the x values of interest. So we want to add up all of the products of the two functions over all the x values of interest. That's just us describing the integral of a product of two functions, right? So this is my first example of measuring sameness right here. It's kind of weird to come up with a numerical measure of how similar are two functions. In this case, we did a graphical kind of visual idea, and it was related to trig functions. Now instead, let's look at an algebraic example, and let's look at some exponential functions. So consider the function e to the 2t and some generic function, e to the st. This is very similar to what we just did above, right? We took a known trig function above and then some generic trig function that just wasn't the exact same as the other one. So consider the function e to the 2t and a generic exponential e to the st. What algebraic function? So now instead of asking for like an operation, like an integral of the product, I'm asking you for a function. What function might measure the sameness of these two functions in terms of s? And here's the thing that I'm thinking. And again, you should maybe stop and think about this for yourself. What I'm thinking to myself is this. When s is very far away from 2, I want to be getting very small numbers, indicating that when s is very far from 2, there is very small similarity between the two functions. However, as s gets very, very close to 2, I want to be getting very, very large numbers, indicating a lot of similarity between the two, right? So let me say this here. When s is far from 2, I want small outputs. Conversely, when s is near to 2, I want large outputs. So my question to you is, just based on our our typical slate of algebraic functions that you learn in college algebra, what function could you come up with in terms of s that's going to give and maybe some form of measurement that kind of has this large and small type of output like we want, where when we're far away from 2, we get small numbers, and in either direction, and that's important here. And the closer and closer we get to 2, the larger and larger our output becomes. I'm thinking here that this sounds to me like I'm describing maybe some asymptotes there in a sense, right? Whereas the further you get away from 2, the less and less similar we are. So as s goes off to infinity, our similarity drops down to 0. Conversely, as s approaches 2, I want our output values to be getting perhaps like infinitely large. We want to have large outputs when we are very, very similar. It sounds to me like I'm just describing a rational function that does experience both horizontal and vertical asymptotes out there. So what I'm thinking to myself is a decent function that does something like this would be something like 1 over s minus 2. You should notice here that when s gets very far away from the number 2, positive or negative direction, we end up getting very, very small numbers close to 0. When s gets really, really, really close to 2, we end up getting very, very large numbers as we approach that vertical asymptote right there. So this seems to me, and I'm just making stuff up with this first and second example right there, being like, here's some things that might be reasonable for what we're thinking about right here. I'm just kind of trying to estimate how do you come up with a function or a description of a calculation that's helping us measure sameness between two functions that are maybe related, two trig functions, two exponential functions, right? So it seems like we've got some ideas here of how some of this maybe is going to work, all right? So, because two common functions to measure sameness against are trig functions and exponentials in our two examples that we've just done, what we're going to consider is this integral transform right here. All right? So here's our deal. This integral transform, you should first recognize this to look a whole lot like the integral setup that we did right here, where instead of having y of t and sine of t, we have a y of t and an exponential. However, in this exponential, this z term right there is a complex number. And since it is a complex number, by Euler's identity, you know that that's going to help us capture both exponential and periodic behavior right here. So when I think about this integral from e to the negative zt y of t dt, what this is really giving me is it's really giving me e to the negative a plus bi t y of t. And what you know from our look at our complex eigenvalue scenarios is that this is going to be like an e to the negative at and an e to the bit, negative bit, y of t. And so really, we typically split this up into two different transforms, one including the real parts, one including the complex parts. Again, notice that this e to the negative at is capturing exponential behavior. And the e to the negative bit, which is going to be equal to cosine of bt plus I sine bt, captures periodic behavior. So typically, we consider the two settings associated with this transform separately here. And so we will look at here, let's move that down a little bit. So we are going to look at there are then two different transforms associated with this here. Sorry, let me write this in exactly the same format. I just want our notation to match right here. So one possible transform that we could look at would be y of t e to the negative at dt. That's the real component of z right there. So this would capture our exponential behavior. Alternatively, we could look at our y of t e to the negative bit, and this would capture our complex behavior, our periodic behavior right there. This is what we refer to as a Laplace transform. This is what we're going to talk about this week. This guy over here is another thing that you guys are all going to study when you go take your next calculus course out there. This is called a Fourier transform. So these are two different integral transforms that help us measure similarity between two functions, right? So our thing of interest in this chapter is going to be the Laplace transform, but it is very closely related to this thing called the Fourier transform, which even though I'm assuming most of you don't academically know about Fourier transforms, it's a very, I don't know, there's a million nice clickbaity videos out on YouTube about awesome things that people do with Fourier transforms. Slightly more complicated. We're not going to cover them here, but very closely related and help us talk about rotations that describe certain shapes. So what I want to do is take a look at computing a Laplace transform in association with a function. So let's try it with the exponential example from above. Let's determine the Laplace transform. Oh, and by the way, I'm going to stick some 0 to infinities on these integral signs right here. Integral or Laplace transforms associated with this function e to the 2t right here. So that was the one that we suggested a minute ago. Let's compare e to the 2t to that e to the negative at right there and see what we end up with. So what we're going to do is I'm going to call this here my capital Y. For some reason, it's very typical to use the letter S as our parameter right here. So rather than A, I'm going to use S in this example right here. And that's a typical thing to do in association with Laplace transforms. I don't know why that letter became associated with it. But what we're going to do is take our integral from 0 to infinity of e to the 2t. And we want to know how it relates to e to the negative st dt. Well, if I'm going to go ahead and evaluate this integral, the very first thing I notice is these are both exponentials with a base of e with a t up in the power. So it really looks like this is just the integral of e to the 2 minus s t dt. And when I go ahead and try and evaluate that, I know that I've got this bounded infinity right there. So I'm going to go ahead and be responsible with my bounds and say this should be the limit as b goes to infinity of, and it looks like I'm going to get a 1 over 2 minus s times e to the 2 minus s t evaluated from t equals 0 to t equals b. And let's take a look and see what this looks like right here. It looks like to me we're going to get the limit as b goes to infinity of, and in this case right here, I am seeing that the 1 over 2 minus s doesn't have anything to do with the b. So I'm going to actually stop for a second and pull that stuff out in front of the limit since it's not affected by the limit. Limit as b goes to infinity of e to the 2 minus sb. And notice that when we plug in 0 for t, we're just getting 1 out from our exponential expression right here. So I'm going to get a minus 1 right there. Now, you should notice that evaluating this really depends on the size of 2 minus s. All right, and here's what I'm seeing. If 2 minus s, if this 2 minus s value is going to be less than 0, or sorry, I want to phrase this differently. Sorry. I want to talk about just the size of s right here instead of 2 minus s. If we see that s is going to be less than 2, so s is less than 2. So what that means to me is that when I do 2 minus s, I'm going to get a number like, if s is 1, for example, then 2 minus 1 is 1. We're going to get just e to the b, and as b goes to infinity, this value is going to diverge off to infinity. Right? On the other hand, if we see when s is greater than 2, then we're going to see that this 2 minus s is going to be a negative value. So as b gets infinitely large, we're looking at e to the negative infinity, which is just going to be 0. And so we're going to get 0 for the limit. In this case, then, notice that we would get, so this value is going to go to 0. So all we'd be getting is 1 over 2 minus s times negative 1, which would be 1 over s minus 2. Does that look like a function you've seen a few minutes ago? And finally, notice that if s is equal to 2, if s is equal to 2, then we're actually getting 0 right here. And it seems like we're going to get sort of a limit that we can't really evaluate right here. We've got e to the 0 times infinity right there, and that 0 times infinity is going to leave us at sort of an undefined. You should also notice that 1 over 2 minus s will be undefined. So let's just say here our expression is undefined. So basically what I'm concluding here is this. To perform this Laplace transform, right, of this e to the 2t times the unknown function e to the negative st, it seems like what we're going to get is the only time that we get a convergent value for this integral is when s is greater than 2, and the value that the integral converges to is 1 over s minus 2. So this seems to be exactly in line with what we were looking at a minute ago, which was that we proposed that this product, the integral of the product of the two functions, is a way to measure the similarity, and that we were expecting to get out rationals that have a difference in the denominator. And we saw that we did set up an integral that looks like this, and we did get out a function that looked exactly like that, in fact, right there. Let's kind of say some things about this. We notate the results of this computation as saying that we computed the Laplace transform, so that's my script L, of e to the 2t, and what we ended up getting was 1 over s minus 2, and that was only true when s was greater than 2. Right, so that's how I would notate the result of that. So you're going to see this Laplace operator right here going on this week. That's my script, like a cursive L. And for some reason, the Laplace operator always uses brackets rather than parentheses to indicate that we're taking the Laplace transform of the quantity inside of the brackets right there. You should notice that this agrees with what we had said, which is that e to the st looks more and more like e to the 2t as s approaches 2. And as s approaches 2, we are getting large values out of this. When s is far away from 2, we're getting small values out of this. This does seem to be a good measure of sameness right here. You should also notice that this was a very specific example right here. So if we looked at the Laplace transform of a more general e to the at, it should be the fact that the Laplace transform of e to the at is just going to be, and notice 2 is just like treat 2 as a placeholder right here. It should be 1 over s minus a whenever s is greater than a. And even more so than that, you should notice the very special case of when a is 0. The Laplace transform of e to the 0t is really just the same thing as the Laplace transform of 1. And when I plug in 0 for a here, it should just be giving us 1 over s whenever s is greater than 0. So I am going to go ahead and kind of mark these off as being sort of special right here. One of the things that we're going to want to do over the course of this section and the next section is identify all of the Laplace transforms that we know. All right, so here is one of our given Laplace transforms that we know and are going to use. Here's another one that's kind of one on our list of known Laplace transforms. It turns out that identifying the value of Laplace transforms is something that we want to reuse over and over and over again. So this is one of those things where as soon as we've done the calculus once to arrive at the value of a Laplace transform, this sort of just gets put in a list of known Laplace transforms that in the future we can just say, oh, I know what the Laplace transform of e to the at is. It's 1 over s minus a. And I don't need to see that calculus work from you ever again. And that's important because what we're kind of trying to do here is say, listen, a lot of times when we solve differential equations, or when we attempt to solve differential equations, we run into some calculus issues where we just literally can't perform the integration required. What we're trying to do here is we're trying to move the difficult calculus operations into applying the transform. Once we've transformed our differential equation, all that we're really going to have to do to solve it is just algebra steps, all right? So we're placing the difficulty of the algebra not in doing the solving, but in doing a transformation. So we're transforming the space that we live in. Instead of being in a YT space, in our regular space, we're going to transform into Laplace space. It takes calculus to transform into Laplace space, but once we're in Laplace space, we can do all of our manipulation. It's going to work out that it's going to just be algebra. We're going to see that in a second. Then all we're going to need to do is get back out of our Laplace space, back into our regular space, which again is going to take calculus. But the thing that we're going to end up seeing is that the calculus to transfer into Laplace space and the transfer to transfer out of Laplace space are, in general, typically going to be simpler than actually trying to do the direct solving of a differential equation using calculus. And we know that, like, as soon as we have integration to do, you should be immediately like, well, what are the odds we're actually going to be able to do it, right? So that's why it's really important that when we do some new Laplace transforms here, that we sort of say, cool, I own that one now. That is now a Laplace transform that I have access to, where I don't need to go back and revisit the calculus anymore. The whole point of this is we're trying to find a way to avoid doing calculus while doing calculus problems, right? So, and I'm just kind of saying that in a short paragraph here. Our mission is to apply Laplace transforms to differential equations to aid in finding general solutions. You should notice that if we take, and by the way, I'm just going to use this abbreviation a whole bunch in our notes here, LTs, Laplace transforms. If we take Laplace transforms of differential equations, what that means is we're going to need to know how to apply a Laplace transform to a derivative of a function, right? So some other things that we'll need to know the Laplace transform of is not just functions like e to the at and constants like 1. I also need to take the Laplace transform of a derivative. So again, our whole point is to say we're going to take a differential equation and we're going to transform it to live in a different space. Instead of being parameterized by t in our traditional space, it's going to be parameterized by this s that you're seeing floating around here over in Laplace space. But if what we're going to do is just start by taking Laplace transforms of a differential equation, that means that there's going to be a derivative somewhere inside of the thing that we're taking the Laplace transform of. So I'm also saying right now, it seems like another thing I need to be able to understand the Laplace transform of is dy dt, right? Because we're going to have those floating around within our differential equations. That's the definition of a differential equation, something that has a dy dt in it, right? So let's check it out. Let's find the Laplace transform of dy dt. So my goal is to take the Laplace transform of dy dt. What we've seen is that according to our definition of the Laplace transform, that just means we want to take the integral from 0 to infinity of dy dt times e to the negative st dt. So what I'm seeing I have right here is I have the integral of the product of two functions, and immediately I'm like, oh crap, I don't know if I'm going to be able to do this, but I'm thinking to myself, what do I typically do when I have the product of two functions in my integrand and I don't quite know what to do? Very often our good move right here is integration by parts. So let's go ahead and see if we can parts this thing to success. So I need to pick a u and I need to pick a dv right here. And the thing that I'm thinking is that dy dt, that's already in derivative form, so it seems to me like that would be a good choice for dv, because I would take the integral of dv to find v, and I can find the integral of a derivative right here pretty easily. That means to me that our choice of u should be the other parts, the e to the negative st. So I'm going to go ahead and do u being e to the negative st. That means that my du must be negative s e to the negative st. I'm going to let my dv be our dy dt dt, which you should notice is just dy, and therefore our v is simply going to be y. Right? So let's go ahead and apply this setup for our integration by parts to the integral at hand right here. So I want uv, which is going to be our function now, and I want to remind you that y is a function of t here. So this is going to give me y of t, that's u, times So we're going to get uv, oh, sorry, that's v, times u, which is e to the negative st. Remember that when we apply integration by parts to an integral that does have bounds, we are evaluating those bounds here. So this is going to be t equals 0 off to t equals infinity. I'll put that in quotes because we should probably set up a limit statement that goes with that. Minus the integral of v du. So I'm going to get a v du. V du. So I'm noticing here that there's a negative in association with this, so that's going to turn that into a plus sign right there. I'm seeing that we have a constant coefficient of s, so I'm going to pull that out in front of my integral here. And what we have left is y e to the negative st from 0 to infinity dt. So did this help us at all right here? Well, one thing that it looks like we need to go ahead and do for ourselves is that we need to know how do we evaluate this expression right here. And like, did we even help ourselves? Like, is this integral even doable for us right here? I don't know what to do with y e to the negative st right there. Maybe more integration by parts, or what are we going to do? Let's write this guy out here first. This one looks to me like this should be the limit as b goes to infinity of let's see here. We want to go to this b as our upper bound right there. So this is going to be y of b e to the negative sb. That's plugging in infinity. Minus, I want to be plugging in 0. So that's going to give me y of 0. And then just e to the negative 0 is just going to give me 1. So I think I can just leave that as y of 0 right there. So what's happening over here? I've got s times some integral, and I don't really know what to say about that integral right there, about like computing it. But wait a minute, what structure does this integral look like to you? Y times e to the negative st. Y times e to the negative st. That's literally just our definition of the Laplace transform of the function y. That's all that is right there. Here is our Laplace transform of the function e to the 2t. That's just the Laplace transform of y right there. I should maybe write this right here. This is what we call our Laplace transform of y of t. Right? So I'm not going to compute this. I'm just going to call it for what it is. This is just the Laplace transform of y of t. And that's good because what we've now done is we've taken the Laplace transform of a derivative, and what we've gotten out is, okay, we still need to talk about this right here, but we've gotten back just some terms that involve just the Laplace transform of the original function. And remember, when we're solving a differential equation, our goal is to solve for y. So it looks like one thing that happened here is that by applying the Laplace transform of a derivative of y, it actually just gave us the Laplace transform of just y. So even though we're still in the Laplace space over here, in a sense, we've gotten closer to solving for y because we're no longer having the Laplace of the derivative of y. We now just have the Laplace of just y, right? So we're a smidge closer right there. Now what's going on over here? Well, you should notice that as b goes to infinity, we're going to get e to the negative infinity, and this is going to end up going to 0. And so it looks like all that we survived from this limit expression right here is just negative y of 0. So it looks like our Laplace, oh, let me just write this as an equal sign right here. It looks like what we're getting out in total for our Laplace transform of dy dt is just negative y of 0 plus s times the Laplace of y, right? Y of t right there. I'll just shorthand it to y right there. And again, here's the really important thing. By applying the Laplace transform to the derivative of a function, it actually just gave us back. We need to know apparently about the initial condition that's associated with y, but also we just now have the Laplace transform of just the original y. So you should notice that this handled the calculus step for us right here. We went from a calculus operation on y to not a calculus operation on y. That's the small powerful thing under the hood that's happening here with our Laplace transforms. So it looks like we have another known Laplace transform that's available to us now. That means to me that it's now appropriate for me to go ahead and put this thing in its nice little pink box right here so that we can reference back to this guy later here, right? What I should say right now is, as of right now, you should be a little bit confused as to what we're doing and why we're doing it. But again, I'm trying to I don't know. This is sort of one of those things where I can tell you what our goal is with this setup right here, but until you actually see it in action, it doesn't really mean much to you. But again, what our goal here is to say, sometimes differential equations require calculus. That's straight up impossible for us to do to directly solve them. If instead we convert our differential equation into the Laplace transform of a differential equation, it seems like what will happen is our derivatives are no longer derivatives. Now this means I could maybe solve my Laplace transformed differential equation for the Laplace transform of y. And so it's like we've solved for y, but we've solved for y in a different space than where we started, right? It's in Laplace space in which we've solved for y, not our original space. So it seems like this helps us take the Laplace transform of a differential equation, solve it for the Laplace of just y, which we know we're going to get every time we take the Laplace transform of a derivative. Then all we'd need to do is get back out of our Laplace transformed space back into our original space, and we would have our equation for y right there. It's exactly what we're going to do. All right. So this is saying rather than going straight from a differential equation in y to y, we're instead going to take our differential equation in y to Laplace space differential of equation for y, solve for the Laplace transform of t, then undo our Laplace transform of y to get back into just y right there, right? And so again, what we can see happened here is we've replaced a calculus operation in y, dy dt, with an algebraic operation in y, negative y of 0 plus s times Laplace of y right there, right? So some other nice things that we get here. So it's also going to be the case that because Laplace transforms are just integral transforms, it's just us applying an integral operation here. What that means is that we get some of the really nice properties that are associated with integrals, such as the fact that if we take the Laplace transform of c times some function f, that constants aren't affected by integration, right? So we know that we can just pull constants out front. So because a Laplace transform is an integral operation, that says constants can be pulled out front. The other thing that we know about integrals is that if we take the integral of the sum of two functions, that we can go ahead and split up that integral over, split that up into two different integrals, right? So it's also going to be the case that the Laplace transform of the sum of two things, we can pull that sum out of the Laplace transform, and there's no real difference, right? The integral of the sum of two functions is the same as the sum of the integral of the separately, right? So that's just saying because Laplace transforms are integrals, they get the properties that integrals have, which is that constants can come out front. We can separate them by addition or subtractions. Maybe I should write this as plus or minus right there. All right, so now that we've kind of done some of our upfront work to look at what does it mean to do a Laplace transform, none of that means anything to you unless you've used a Laplace transform for a meaningful purpose. So I'm going to give us now a differential equation, and what I want to do, our goal with all of our differential equations is we want to solve for y, but we can't quite do that yet. Instead, let's at least get as close as we can. Let's solve for the Laplace of y. That's going to be very, very, very close. And then we'll ask ourselves, is there any way we can undo this Laplace transform to then just get back just y? So let's go ahead and do this here. So what I'm going to do is I'm just going to take our differential equation. And notice, I want to point out one thing real quick. We have to have initial conditions when we use Laplace transforms to solve differential equations because we're always going to have the Laplace of a derivative when we're solving differential equations, and it's always going to be the case that that's going to pop out for us an initial condition of 0, a y evaluated at 0. So we need initial conditions every time we're doing Laplace transforms out there. So that is given right there. So what I want us to do is almost solve this differential equation for y. We won't know how to do the last step, but we can get as close as we can right now, which is solving for the Laplace of y. Right? So what I'm going to do is I'm going to go ahead and take the Laplace transform on both sides of this differential equation. Now, a couple things I want to do right up front. One, I know what the Laplace transform of dy dt is, so I'm just going to copy that down from what we saw above. Two, we just stated that because Laplace transforms are integrals, really, that means that constants aren't affecting our Laplace transform, and sums or differences, we can split it up over those things right there. So let's see all the things that we want to write for our next line right here. So one, I know that the Laplace transform of dy dt is negative y of 0 plus s times L of y. That's negative y of 0 plus s times the Laplace transform of y. That's what goes on the left right there. On the right, I know I can split this thing up over addition and subtraction, and I know that constant multiple of 4 doesn't have to be any part of the actual calculus that's happening here, right? So I'm going to write this as the Laplace of y minus 4 times the Laplace of e to the negative t. Remember, our goal really overall is to solve this differential equation for y. The best we can do right now is to solve it for L of y. So this L of y is sort of our goal that we're looking to end up being solved for. The only other Laplace transform I see that we have is the Laplace transform of e to the negative t, but I have great news for you. We know how to handle Laplace transforms of exponentials. We already did that calculus once. We don't have to do the calculus again, right? So let's go ahead and see what this is going to look like here, right? We want to solve for L of y. We want to replace this Laplace transform with its known value, right? So here's what I'm thinking. Let's get all of our L of y terms on the left, so all of our not L of y terms on the right. So I'll do this algebra step first. So I'm going to get S Laplace of y minus the Laplace of y that I'm subtracting over from the right should be equal to, and I'm going to move y of 0 over to the right, so I'm going to get a positive y of 0 over here, minus 4 times the Laplace transform of e to the negative t. So that was just my algebra step to shift my terms around. My goal is to solve for the Laplace of y, so I'm going to factor it out from our two terms here. It looks like I have an s minus 1. This should be equal to, notice here I know what y of 0 is, it's just 1, right? So that's 1 minus 4 times, I know what the Laplace transform of e to the negative t is, right? So e to the negative t up here, that's like a is negative 1. E to the negative t is where a is negative 1. So I should be getting 1 over s plus 1 because that negative is built into the formula right there. So 1 over s plus 1 is what we're getting from this Laplace transform. And so I've basically solved for L of y here. The Laplace transform of y should be equal to 1 over s minus 1 times 1 minus 4 over s plus 1, which I could then write as 1 over s minus 1 minus 4 over s minus 1, s plus 1. So now here's the situation that we're in. We've done almost what we really want to do, right? And what we've done right here is, and I'm going to kind of draw our diagram right now. That's going to help us kind of visualize what we're doing here. In our diagram here, we're starting with a diffie q in y t. And what we want to do, what we want to be able to do that we typically can't do, is we want to just solve for y. And that would get us to just being right here. Y of t equals, right? That's that location that we'd like to get to. But the problem is that we very often, I wrote this in red because often we can't just do the calculus to solve a differential equation. There's so many calculus hangups that we end up hitting. So instead, what we're doing now in this case right here is we're instead saying, okay, let's take the Laplace transform. Let's take the Laplace transform of the differential equation. And this gets us a differential equation in, this gives us a algebra equation. That's the important part right here, is we ended up only doing algebra to solve for L of y. This gives us an algebraic equation in terms of the Laplace of y and s. Here, now we can do the solving. Notice that the solving is our vertical oriented part in this diagram right here. I can easily algebraically solve for L of t, or L of y. Oh, I guess according to my color scheme, I should be writing that in green. Please solve for L of y. And so now what we have is now we're now in the situation of saying L of y equals, that's now the scenario that we're in. We instead of having solved for y, we've solved for the Laplace of y. So the remaining step that we still need to be able to do is we need to undo the Laplace transform. So what we just did step 1 by taking the Laplace transform on both sides, and we did step 2 by algebraically solving for L of y. So we started here, and we're we're currently right here. Our last step is we still need to undo the Laplace transform to actually get to a y of t equation. So that's our remaining step that we still want to be able to do. And I'm going to do just a little bit more color stuff right here. Is we applied the Laplace transform to the differential equation. This is sort of like our step one, and this is like our step one. And then we solved the differential equation for L of y. We still need to do this last step now to take us from the Laplace transform of y to being actually just y of t. So it seems like we're taking a longer route here, but the whole point is that solving for y directly is very rarely actually doable. Only in our very nice scenarios does that ever work out, because the calculus often is just literally impossible, right? But if we know some Laplace transforms, then the calculus for those has already been done. Like, we didn't do any calculus right here, but we've gotten rid of the derivative. That's the important part. The calculus happened under the hood because we already handled the calculus here. We already handled the calculus here, right? We did that calculus right there, right? So this is one of those things where we can just do the calculus once for a known function like e to the negative at or for dy dt, and we never have to do the calculus with that function ever again. We just get to use those old results right there, right? So we still need to figure out how to undo this Laplace transform. So we haven't solved the differential equation. We want to find y, but instead we found the Laplace transform of y. We now just want to undo the Laplace transform. Fortunately, it can be shown that there's a guaranteed uniqueness of the inverse of Laplace transforms as long as the transformed function is continuous. So all that's saying to me is the Laplace inverse of some capital F being equal to lowercase f is always going to be equivalent to f being equal to, all right, that was a bad one right there, the Laplace transform of our lowercase f right there. All right, so we're always going to get the case that we can just undo these in the same way that we did these. All right. Further, because Laplace transforms are integral transforms, they are going to be linear operators. And all that really is saying is the same stuff that we set up there one moment ago, which is just that we can kind of, pull these apart by addition, subtraction, and constant multiples. So a times the Laplace transform of x plus b times the Laplace transform of y. All right, so we can always separate these things by addition, subtraction, pull out constant multiples out there. From this, it's going to, because our inverse Laplace transforms are guaranteed unique, it must be the case that this inverse Laplace operator is also a linear operator. So it's also going to get those same properties out there. So Laplace inverse of ax plus by is also going to be a times the Laplace inverse of x plus b times the Laplace inverse of y, right? And that's really important. The fact that we're able to rip apart our inverse Laplace transforms here is going to be necessary for this to actually be any sort of meaningful process to us. So it seems to me like, here's what I'm seeing. We want to undo this Laplace transform by just applying an inverse Laplace transform, but I don't want to do the calculus. I just want to say to you, hey man, listen, do you know what function we took the Laplace transform of if I got out 1 over s minus 1? And you should say to yourself, hell yeah, I know what we did. I know exactly this structure right here. You get out stuff that looks like 1 over s minus 1 when a is 1. That is literally the function e to the t that we must have taken the Laplace transform of to get to 1 over s minus 1 must have been e to the t. So when I apply my inverse Laplace transform to both sides of this equation right here, I'm going to get back just y on the left. I'm clearly going to get just an e to the t for this term that we're looking at right here. And what I don't know, though, is I don't know an inverse Laplace transform for this expression right here. But if we did some partial fraction decomposition and ripped that up into two different fractions, then I would. Certainly, it would be back in that structure of those exponentials once again, and I can just undo the known structure of that Laplace transform once again. So let's go ahead and partial fraction decomposition our expression for L of y and then attempt to solve. Right? So what we want to go ahead and do is do the partial fraction composition here. This should be equal to a over s minus 1 plus b over s plus 1. I'm going to multiply by the whole denominator on the left here. It's going to give me a times s plus 1 plus b times s minus 1. Rather than having these grouped by the a's and the b's, I want these to be grouped by the s's and the constants here. So I'm now going to write this as 4 equals, how much s stuff do we have? We have a plus b of it. And then the next grouping is how much constant stuff do we have? We have a minus b of it. So that says to me that a plus b needs to be equal to 0 because there's no s parts on the left, so a is equal to negative b. It also needs to be the case that a minus b is equal to 4 because that's how much constant stuff we have on the left. By doing a quick substitution here, it looks like a plus a is equal to 4, and so a is going to have to be 2, and therefore b is going to have to be negative 2 for our quick little partial fraction decomposition here. So it looks like I can now write this as L of y equals 1 over s minus 1 minus, and a was positive 2, so 2 over s minus 1. And then that was a plus sign that's right there, but we're really getting a negative 2 for b, so that's going to be a minus 2 over s plus 1. And so now it really looks like just a little bit of simplification because I do have two terms that have the same denominator here. Here's two different s minus 1s. So overall, there is negative 1 copy of the 1 over s minus 1. And so now I'm going to go ahead and I'm going to take my inverse Laplace transform right here. So now I'm going to do an inverse Laplace transform of the Laplace transform of y. That's just going to give me back y right here. I'm going to take the inverse Laplace transform of this whole side over here. But I'm going to do the typical things that I would always do in a calculus setting, which is say, oh, those constant multiples don't affect my calculus. Sums and differences, we can split them up over that. So I think I want to write this as negative Laplace inverse of 1 over s minus 1 minus 2 times the Laplace inverse of 1 over s plus 2. And now I'm remembering that I know the structure of both of these. We've gotten out things like these two expressions from Laplace transforms, so I should know what we're going to get out from the inverse Laplace transforms by going in the other direction. So 1 over s minus 1 is our first one. Let's scroll back up and remember. 1 over s minus 1 says a is equal to 1, so that's just going to give us e to the t. And when I say it's going to give us e to the t, there was a negative sitting out front of it, so we're getting negative e to the t. The other one right here, it looks like I'm going to be getting a minus 2 right here. Oh, wait a second. Sorry, I'm realizing right here, check this out. This negative should have distributed through and to make that positive, so that's actually a plus sign right there. I was like, wait a minute, I didn't get two negatives, did I? So there we go. That's all positive stuff right there. So I'm going to get plus 2 times. Now 1 over s plus 2, let's go back up and take a look. 1 over s plus 2. If we're getting s plus 2 on the bottom, that means a needs to be negative 2. So it should be e to the negative 2t is what we took the Laplace transform of to get there. So e to the negative 2t. Wait a minute. Did I? Oh, okay, sorry. I'm being dumb right here. That wasn't a 2 this whole time. That was just a 1. I got all excited about the 2 up there in the numerator. So let me try this whole thing again right here. Those were 1s. Sorry for these little typos here. 1 over s plus 1 should be giving us a being negative 1, so it's just e to the negative t. And boom, here we are. Remember that we saw that the Laplace of e to the at was equal to 1 over s minus a. So it must be the case that e to the at is equal to the Laplace inverse of 1 over s minus a. And I just used that twice in that setting right there. And we have now solved this differential equation without kind of doing any calculus, basically, right? We did the calculus once up front, and we never have to do it ever again, which is super awesome right here. So now we've seen how this whole route goes right here, right? We're going to take a Laplace transform of the whole differential equation. We need to know how to apply the Laplace transform to all the functions that are on the inside. So you should now realize we're going to want like a whole catalog of Laplace transforms out there. We got exponentials, we've got derivatives, and we've got constants. We can take the Laplace transform of 1. Remember, that was a special case, the one that we saw up above. So that's all we've got, constants, exponentials, derivatives. We're still going to want things like linear functions, trig functions, all of our other families of functions that we might end up out there. There's a Laplace transform for all of them, right? So we're going to take the Laplace transform of the whole equation. We're going to then, instead of doing calculus to solve, we're just doing algebra to solve, because in Laplace land, you can manipulate things to solve for the Laplace of y without doing calculus. Then we need to undo our Laplace transforms. But the great news for us is that inverses are unique, meaning all the rules that we find of how to apply a Laplace transform, we can always just go backwards to undo a Laplace transform, saying, ooh, 1 over s plus 6, that looks like the structure of the Laplace transform of an exponential function, so I just got to figure out, oh, it should be e to the negative 6t. There we go, and we're done, right? So this is our Laplace transform route to solving differential equations, is we're transforming ourselves to be in a different setting, s and L of y rather than t and y. We're doing all the math over there, but then we need to get back into our original setting. And so we're doing Laplace transforms to leave and Laplace transform to get back. But all the work is happening in our transformed space. That's the important thing. Transformed space, we're doing algebra instead of calculus to solve. That's what makes this so dang powerful, is we're roundabouting having to do the calculus by just using a catalog of already done calculus from other people, or that we've done for ourselves here. So it seems like a process is apply the Laplace transform, solve for L of y, and then apply the inverse Laplace transform. This is good because we're replacing our calculus steps with algebra steps. This is bad because we're dependent on recognizing known forms of Laplace transforms, which themselves require some challenging calculus to find. However, if you are given a table of known Laplace transforms, there it is. If somebody already did the calculus for you, then this becomes a lot nicer. And this should sort of feel like cheating to you, and I want to explain to you briefly why it's not. The reason why it's not is because there's like a billion different ways that all of our differential equations could come to interact with one another, all the terms interacting with one another. If you've got a t squared somewhere and an e to the 6t somewhere else and a sine of t somewhere else, you've got to do calculus that's going to involve all of those collectively at the same time. When we do Laplace transforms, on the other hand, because we get to split this up into each of the groupings, that means that we're only ever dealing with the Laplace transforms of each of those functions one at a time. And that makes it much, much, much easier for us to go ahead and do the solving process. That means that all we need to know is just a general rule for a Laplace transform of an exponential, Laplace transform of a polynomial, Laplace transforms of constants, linears, Laplace transforms of trig functions, logarithmic functions, and we can individually, one by one, apply them to the terms that we see in the differential equation. So that says to me, it's not like we need to come up with the Laplace transform of every single possible differential equation setup that we ever might see. We really just need to know all the Laplace transforms for all of our basic algebraic functions that ever appear in our differential equations, just individually, standalone, and we can apply them individually, and that's why this is going to work out for us. So in our next video, we are going to look a lot at a table of Laplace transforms. If you want right now, just look up Laplace transform table, and the internet will provide you with thousands of them, because it's incredibly typical for people to just use a reference table to know the Laplace transforms that we want to apply, and consequently that gives you by default all of your inverse Laplace transforms as well. So let's go ahead and look at another example here. Earlier in the semester, we did an example of a differential equation describing the voltage across a capacitor with an RC circuit. Let's revisit that example here. So here's our example that we're going to do here. I got to draw my RC circuit diagram. I didn't do that. What we want to do is we want to find an equation for the voltage across a capacitor at time t. So at some time in the future t, how many volts are going across a capacitor within an RC circuit? Once I draw the RC circuit, that'll make a little bit more sense. And here's the letters that I'm going to use to represent some things within this RC circuit that we're seeing right here. So let's go ahead and draw our diagram and talk about how this is going to work here. So in our RC circuit diagram here, we're going to have, here's our battery that's providing us the voltage right here. It's got our positive end and our negative end right here. Leaving the battery, we're going to hit a resistor. It's our typical notation for a resistor in an RC circuit diagram. And it's going to lead to the capacitor that's on the other side over here. And our goal is to say, given how much voltage is coming out of the battery that's crossing the resistor, how much voltage is going to end up crossing the capacitor right there. So this is our V of t right there. And what we want to know is what is the voltage crossing the capacitors. That's our V of sub c of t. So we want to find this. So notice real quickly, there are two different V of t's in this equation. One is the voltage that's coming out of the battery. But because it's going to have to cross a resistor, it's not necessarily equal to the voltage that's going to be crossing the capacitor right here. Right? There's going to at least be like a delay in there, right? We have the amount of resistance, we have the amount of capacitance. I cannot stand it when Microsoft Word red underlines words that it agrees are not misspelled. Get away out of here, red underline. So all of you guys, I know that you're all going to go take your electrical engineering classes, and in those electrical engineering classes, you're going to derive the differential equation that relates each of these quantities right here. That's a descriptor of an RC circuit, and this is the differential equation that relates all of those quantities right here. You can see that the capital V of t is the voltage that's coming out of the voltage source. By the way, this should feel a little bit to you like a forcing function for a harmonic oscillator. This isn't a harmonic oscillator, but we still have like some components on the left, and sort of like the force that's being applied to the system, the voltage that's being introduced into the system by the battery is a separated term off onto the right here. And so before we start solving, let's give ourselves some values for some of these parameters right here, and let's stop and think about what we should expect our answer to look like before we go hunting for our answer. All right. So we're going to let R be 1, and we're going to let C be 2, just to give ourselves some numbers in here for R and for C. All right. And let's assume, and just to think about this, let's assume that the voltage source that's being emitted from the battery is constant, which is hopefully going to be the case for any good battery, and it's going to be putting out 3 volts here. What is the equilibrium state then for the voltage across the capacitor, and how would you classify it? So what I'm seeing here is if R is 1 and if C is 2, then we're just going to get 2 dV dt. And by the way, I'm just going to write V sub C as just V because we're about to not write V anymore. We're just going to let it be 3. This should be plus V equals 3. So if I rewrite this, this looks to me like 2 dV dt equals 3 minus V. To find equilibria, that should be occurring whenever our derivative is equal to 0. When is there no change in the voltage across the capacitor? And that should be telling me 0 equals 3 minus V. And so apparently we're going to come to equilibria when there are 3 volts crossing the capacitor over here. So this says to me, if you like turn the battery on, and it is therefore just constantly emitting 3 volts, what I expect is that the voltage across the capacitor isn't just instantaneously 3 volts, but what I am thinking is that that is going to be where it's going to come to rest eventually. This is where the equilibria is located, and then my question to you would be, how would we classify it? Well, you should notice here that if our voltage across the capacitor, V, starts above 3, starts at like 5 volts, 3 minus 5 is a negative value for dV dt, and so our voltage is going to decrease down towards 3. On the other hand, if our voltage across the capacitor starts at like 1 volt, then 3 minus 1 is a positive number. dV dt is going to be positive. It's going to increase until it reaches the equilibria going on at 3 right there. So our little phase line diagram right here should be indicating that a V of 3 should be a sink. We should be moving towards a voltage across the capacitor of 3 eventually. When you turn on that battery, it isn't just going to have instantaneous 3 volts crossing the capacitor, but we expect that over time, if the number of volts crossing the capacitor was above, it should reduce down to 3, and if it was below, it should increase up towards 3. So I just wanted to get an idea of when we get our final answer had better have this behavior that we're describing before we do any solving, because remember, and as this is our final week of the class, I want to remind you, in most meaningful differential equation settings, you still can't solve the differential equation. It's true that we're coming up with a whole different technique for solving differential equations right now, but we still want to be able to do this qualitative analysis where we say, listen, even if I can't come up with a function that describes this, I can still generally describe what the behavior should be like in the long run. We've come up with that right now. When we find our solution, we expect our solution, the equation itself, the analytic solution, to have the same behavior of what we just described right here with a little bit of a phase line, all right? So let's go ahead and solve this differential equation using Laplace transforms, and then let's come back and check to see that our final solution does in fact agree with the phase line that we just drew right there. I might as well call this then a sink. All right, so let's go ahead and solve this differential equation using Laplace transforms here. So let's just go ahead and hit this thing with a Laplace transform, right? And by the way, I can see immediately that I'm gonna, oh, it is giving me room. Okay, let's solve this bad boy. So Laplace transform of 2 dV dt I'm gonna try and be responsible here with my notation because I know that this is just a weird thing that we're doing here today for sure. This is weird. So I'm going to try and write things out very explicitly here. So one, I'm just plopping my Laplace transform onto the left and right side. Now I'm immediately going to say to myself, well, I know that you can rip apart things inside the Laplace transform. Constants can get popped out front. We can split up addition, subtraction. So I'm going to now write this as 2 times the Laplace transform of dv dt. Um, Sorry, I'm realizing here that we need to have a value. I don't think I gave an initial condition for. Yes, I'm checking my notes right here. I know that we're going to need our initial value of the velocity, the voltage across the capacitor right here. So we'll get that. Let me grab that on my notes here in 1 second. Now, this one, by the way, this is one where I don't feel like any of us think to do any factoring, but I want to encourage you to think about this as that right there. We factored out the 3. And that's because way up above, we did state that we do know the Laplace transform of 1, because that was a special case of our exponential right there. I'll scroll back up and we'll look at that again. But this is a pretty typical good algebra move for us to go ahead and do right there. So what I'm seeing here is, okay, I think I had said for myself right here, and I'll just go ahead and type it out, that we should have our v sub c is equal to 4, right? V sub c at time 0 is equal to 4. So notice what this means. I want to stop since I just kind of added this in here late. Is notice that means we're starting initially with a voltage of 4 volts going across the capacitor at time 0. So that means I'm expecting from our initial condition that should be indicating to us that we are going to decay down to 3 volts, right? So we are starting above our equilibrium value right there. So now that we have applied the Laplace transform and separated everything out to its individual terms, let's go and remember what we're looking for all of these guys. So I'm going to do some scrolling right here. Right? So we want to, actually, no, I'm not. I'm just going to kind of write down what we remember over here. I'm going to kind of put our pink or our purple right there, our mauve, our magenta. What color? What does it call that? It just calls this purple. That's not the color I'd call purple. Anyway, we know that the Laplace transform of dv dt, we solved for this one. We got negative, I wanted to write y right there, but it's a v, negative v of 0 plus s times the Laplace of v. We also found the Laplace of a exponential e to the at was equal to 1 over s minus a. We saw that when a is equal to 0, we get e to the 0, which is just Laplace of 1. And so therefore that must just be 1 over s, because a was just equal to 0 right there. So this is the stuff that we already derived on our own today. I'm just going to be using the first one and the third one over here right now. So let's go ahead and expand this stuff. I think that I have 2 times negative v of 0 plus s times the Laplace of v plus the Laplace of v equals 3 times the Laplace of 1, which I know to be 1 over s. Right? I know that negative v of 0 is going to be giving me negative 4. So it seems to me like I'm going to write this as negative 2 v of 0 minus 2s Laplace of v plus the Laplace of v equals 3 over s. So remember that our goal right now, so let me scroll back up and kind of remind ourselves of our general strategy here. Our general strategy here is apply the Laplace transform to the differential equation. We've done that. Our goal is now to solve for the Laplace transform of that dependent variable that we're interested in. Then we'll go ahead and try and do our inverse Laplace. So we're doing step 2 right now. What I want to do right now is I want to solve for the Laplace transform of v. So it seems like what I've really got right here is I've got the Laplace transform of v. How many copies of it do I have? Well, there's 1 copy here, and there's negative 2s copies there. So I've got a 1 minus 2s is how many copies of the Laplace transform of v I have. This should be equal to 3 over s, and I've added the 2v0. That's plus 2 times 4 right there, because v0 was 4. That was our initial condition that I gave late right there. And so it seems like we have very nearly solved for the Laplace transform of V. So my Laplace transform of V should be equal to 1 over 1 minus 2s plus 3 over s plus 8 is what I'm looking at right here. So okay, I'm seeing, I'm catching my tiny mistakes in here again. You should notice here, I got overexcited about my distribution and I distributed this negative that I shouldn't have because it was inside the parentheses onto this guy right here. That should totally be a plus right there. And so this is in fact a plus and a plus right there. Is that the only mistake that I made right there? No, it is not. The other small algebra mistake that I just made right here is that I was dividing both sides of the equation by this 1 plus 2s in the denominator right here. So that should be right there. 1 over 1 plus 2s is what's multiplying this 3 over s plus 8 that we've got right there. And so it seems like my Laplace transform of v is going to be 3 over s times 2s plus 1 plus 8 over 2s plus 1. All right. So we've now finished solving our Laplace transform for the Laplace transform of v. It is now time for us to go ahead and undo the Laplace transform so that we can just straight up solve for v. Sorry, since I've made some typos here, I'm double checking my notes here now to make sure I'm not being dumb. So what are we going to get right here? Well, my issue is I know how to do the Laplace transform of the second term right here, sort of. I definitely don't know what to do with this s times the 2 times the s plus 1. So let's go ahead and kind of say this. So I need to do my partial fraction decomposition on the 3 over s times 2s plus 1. And fortunately for you guys, although I know that you guys love just watching me do algebra in your calculus videos right here, fortunately for you, I've already done this one. This comes out to be 3 over s minus 6 over 2s plus 1. That's my decomposition of that fraction right there. So now let's go ahead and here's what I actually want to do is I want to reverse that arrow right here and say we can do that. So let's go ahead and take this result right here and say my Laplace of v is really going to be 3 over s minus 6 over 2s plus 1 plus 8 over 2s plus 1. So it looks like before I go ahead and do my Laplace inverse, I can combine these like terms. So I am going to write this as 3 over s plus 2 over 2s plus 1. Now, that 2s plus 1 doesn't quite seem to be of the structure that we know from our inverse Laplace transforms. Remember, these are kind of like the three things that we know so far. There is not a 2 sitting on that s right there, but I think I can just do some constant factoring and get that thing out of there. Right? So let's go ahead and apply this inverse Laplace transform here. So I want to do the inverse Laplace transform of the Laplace transform of v. I'm going to do my inverse Laplace transform of 3 over s plus 2 over 2s plus 1. Over here, that's going to leave me just with the v that we're solving for on the left. On the right, I know that I want to rip this thing apart by addition and subtraction, pull my constant multiples out front. So this is going to give me 3 Laplace inverse of 1 over s. I know how to do that one. Plus 2 times the Laplace inverse of 1 over 2s plus 2. 2s plus 1. And this one I don't quite know what to do with yet, but I think I can figure it out. So let's call the Laplace inverse of 1 over s, because I already know that one. Let's state what we know. Laplace inverse of 1 over s is just 1. I'm just reading my chart backwards here. The Laplace inverse of 1 over s is just 1. So this is just 3 times 1 plus 2 times. Now, what do I want to do with this one? Well, I'm thinking I don't want that 2 to be sitting on the s right there, so let's just go ahead and factor out a 1/2 from this guy. And it's really just 1/2 times 1 over s plus a half, right? So you should notice now, come on, words, get out of there, that we're getting our v equation to be 3 plus, this is 2 times 1/2 times the Laplace inverse of 1 over s plus 1/2. And I think I'm good to go here now. This should be v is equal to 3 plus 2 times a half, clearly cancel. Laplace inverse of 1 over s plus 2. I know that I get 1 over s minus a from an exponential here. It seems like I want a to be negative 1/2 to make this look like what I've got. So I want e to the negative 1/2 t is my inverse Laplace transform here. You should notice that this equation absolutely does suggest that as time goes on, the value of v will always approach 3, regardless of whether you start above or below, because the contribution from this term is always going to decay towards 0, right? So this has the desired behavior of decay towards 3. So what a weird day this is. I'm going to go ahead and anticipate this was not the math that you thought that you were going to be doing here today. This is a really strange idea right here that all of our work is in the algebra. The hardest part of this problem here was doing the partial fraction decomposition that I did on the side that I know that you guys can do and don't care to see again, and is just consulting our chart to see how do we do the Laplace transforms and then how do we undo the Laplace transforms, and recognize that reading this chart from left to right gives you your Laplace transforms, right to left gives you your inverse Laplace transforms, right? So all the work here was algebra, and that is the big idea behind Laplace transforms. They take calculus problems and they convert them into, and I can't highlight it here, but they convert them into algebra problems, right? Where the work was right here, solving for L of V. That was the actual solving step, was an algebra step, not a calculus step. Then we just used our table to undo the Laplace transforms, inverse Laplace transforms. You should see that this does keep on requiring partial fraction decomposition. That is a pretty regular thing whenever we have a lot of exponential stuff pop out in our solutions. And you guys know exponential stuff comes out of tons of our solutions in differential equations. Very, very common thing. So partial fraction decomposition comes up a lot. But like partial fraction decomposition is infinitely better than some arbitrary integral that you don't know if you're ever going to be able to solve or not, right? So again, the big power here is that we took the difficulty of the problem from living in a calculus setting to making the difficulty of our problem living in an algebra setting. And that is objectively an improvement. You can't argue against that being better. I don't care if you enjoy partial fraction decomposition or not. It is objectively a simpler process than some random integral. There's just no way. And a random integral is probably not integrable at all, and you can't even do it, right? So we've shifted the difficulty into algebra land and out of calculus land. That's the big power of our Laplace transforms here. So this is pretty cool, but there's a massive but right here. Both examples that we've done have been linear first order equations, both of which we can solve just by using our integrating factor from chapter 1. So that's one sort of lame thing from today. 2, these had only exponential and constant terms crop up in the solution. Now, the book is really smart. The reason that we've only seen that is because the book did a very good job of trying to keep as much concept only in section 6.1 and as much computation saved until later so that we can kind of like feel out what's happening with this Laplace transform. So the only examples that they throw out in 6.1 are with like a very narrow range of functions, because we don't want to say in 6.1, oh, and here's these 17 Laplace transforms you should know. But if you're really thinking about what we want to be able to do here, think about all the differential equations we've solved this semester, we kind of need lots more Laplace transforms than just the three that we listed in our little block right here, right? Like that's not going to do it to cover the semester's worth of differential equations that we've seen. So in today, we only looked at like a narrow sliver of this, right? We really put the horse blinders on, but that's because this is conceptually a really weird process right here when we've seen it with just a few couple functions here. I hope it's obvious to you that how we want to expand this going into section 6.3 is in two things. One, we want to expand the repertoire of functions that we have available to transform. I want trig functions, and I want some polynomial functions. Even just the Laplace transform of just t, not directly obvious to us right now, let alone things like sine of t, let alone things like sine of a of t or something like that, right? The other thing that seems hopefully obvious to you that we want to be able to do is that most of our interesting differential equations are actually second order differential equations. So it seems like aside from just being able to do the Laplace transform of the derivative of y, I actually want to be able to do the Laplace transform of the second derivative of y. So all we're really going to do in 6.3 is just keep going. We're just going to get more Laplace transforms to be able to solve more differential equations using those Laplace transforms. But what we're going to see is I do want to show you some of the tricks that are involved with computing some new formats of Laplace transforms, right? Building our table of known transforms. But at the end of the day, a lot of these themselves are pretty dang hard. But if some other very smart person has already done all these for you and just put them in a big table of the results that they got, then we can just use their table. And then, therefore, again, all that happens in Laplace transforms is that the hardest part of the math is algebra, and that's all you're ultimately going to end up being responsible for. So in our next and very final video of the semester, in section 6.3, we're going to expand into more functions other than just exponentials and constants, expand into second derivatives and not just first derivatives, but other than that, you're just going to see a bunch more stuff that looked exactly like this video. So 6.3 follows very, very naturally from 6.1. It's just, we're just doing more functions, more derivatives, same exact idea. Our process here of apply a Laplace transform, solve for all of y, apply an inverse Laplace transform is still going to hold. So this diagram right here, to me, this is like the single key idea of what we did here today. And I would encourage you guys, by the way, remember that you are all like kind of wrapping up your calculus sequence right now. All of you are essentially done with your undergraduate calculus sequence. You should be thinking about things in sort of like higher terminology right now, that this is really a scheme for a strategy right here that we have mapped out, that we've diagrammed out. There's lots and lots of these more complicated processes that happen in higher math that it's going to greatly benefit you to be able to diagram what your process looks like and why you're choosing to take certain routes over other routes. These types of diagrams right here, I remember seeing some of these things when I was like late in high school, early in my calculus sequence, and being like, why in the hell is this guy spending all his time drawing these things? And then by the time I got to grad school, I was like, I literally can't do what we're doing if I can't see a mapping of like the structure of our process right here. So I think these kind of things are intensely valuable. So I would, if you don't like this, I would encourage you to take a moment and convince yourself that this is a really good idea of a description of a process right here, and that you should think about lots of your processes in this type of format right here. So that wraps it up for our 6.1. In our next video, our very last video of the semester, we're just going to do more second order derivatives, more different types of algebraic functions out there. I will see you guys for our video on 6.3, second order Laplace transforms. Have a good one, everybody.